Welcome to G Fun Facts Online. Today, we're going on an odyssey into the heart of one of the most captivating mysteries in modern astronomy: fast radio bursts. Imagine a flash of light from halfway across the universe. It lasts for only a few milliseconds, less time than it takes you to blink. But in that fleeting moment, it shines with the energy of an entire galaxy, releasing as much power as our own sun does in 3 days. Then, it vanishes without a trace. These are not the gentle pulses of a distant star. They are the universe's ephemeral fireworks, and since their discovery, they have launched a global astronomical detective story. What could possibly generate such immense power in such a short time? Let's find out. The story begins, as science stories often do, not with a sudden eureka, but with the patient sifting of old data. In 2007, Professor Duncan Lorimer at West Virginia University gave his student, David Narkevic, a routine task: search through archival data from the Parkes Radio Telescope in Australia, looking for pulsars. Pulsars are like celestial lighthouses, spinning dead stars that send out regular beams of radio waves. But buried in data from 2001, Narkevic found something utterly bizarre: a single, incredibly powerful burst of radio waves that lasted for just 5 milliseconds. What made it truly strange was its dispersion measure. Think of it this way: as radio waves travel through the thin plasma that fills the space between galaxies, it's like they're running an obstacle course. Lower frequency waves get slowed down more than higher frequency ones. This means the signal arrives at the telescope smeared out, with the high frequency light hitting first, followed by a rapid downward sweep in frequency. The dispersion of this signal, now known as the Lorimer burst, was immense. It was far too large to have come from within our own Milky Way galaxy. The signal had to be extragalactic, meaning it had traveled for billions of years across the cosmic ocean. This implied a source of almost unimaginable power. For years, the Lorimer burst was a lonely anomaly. Some astronomers were skeptical. They suggested it could just be a weird type of interference from Earth, and they had good reason to be cautious. A similar series of signals, nicknamed peritons, were eventually traced to microwave ovens being opened prematurely in the telescope's staff kitchen. A classic reminder that sometimes the most exotic signals have the most mundane explanations. But the Lorimer burst was different. In 2013, another team found 4 more of these high dispersion bursts in the same telescope data, confirming they were real astrophysical phenomena. The field of fast radio burst research was officially born. As telescopes began to spot more of these bursts, a fundamental divide appeared, creating 2 main categories in the FRB zoo: the one-offs and the repeaters. The vast majority of FRBs seen so far are one-offs. They flash once and are never heard from again. This suggests their origin is some kind of cosmic cataclysm, a destructive event that obliterates its source. Theories naturally gravitated towards catastrophic scenarios: the violent merger of 2 neutron stars, the collision of 2 white dwarfs, or the final collapse of a supermassive neutron star into a black hole, an event some call a blitzer. A huge step forward came when astronomers managed to trace a one-off burst, FRB 180,924, to its specific home. It was found in a massive, relatively quiet galaxy, similar in size to our own Milky Way. This was important because it showed that FRBs can come from very different environments, keeping the puzzle of their origin wide open. Then, in 2012, the game changed completely with the discovery of FRB 121,102. This one repeated. Astronomers at the legendary Arecibo Observatory detected multiple bursts coming from the exact same spot in the sky. This was revolutionary. It proved that at least some FRB sources are not destroyed when they create the burst. Cataclysmic events like neutron star mergers were out for this class of FRB. The source had to be a long-lived, persistent engine. Because it repeated, astronomers could stare at its location with other, more powerful telescopes. They eventually pinpointed it to a tiny dwarf galaxy, a furious nursery of star formation, about 3 billion light-years away. This extreme environment hinted that the source was a young, highly energetic object. The plot thickened even further with a source called FRB 180,916. This one didn't just repeat, it repeated with a clockwork-like rhythm. Astronomers using the CHIME telescope in Canada found that it followed a strict 16.35-day cycle. It would be active for about 4 days, firing off bursts, then fall silent for the next 12 days, before starting all over again. This periodicity was a massive clue. It suggests a mechanism involving orbital motion or rotation. Perhaps it's a binary system, where an FRB-emitting object orbits another star that periodically blocks the signal. Or it could be the wobble, or precession, of a single isolated object whose beam only points towards Earth during a specific part of its cycle. Detecting a signal that lasts for a few thousandths of a second from billions of light-years away is an incredible technological feat. It requires telescopes with a huge field of view to catch a random flash and mind-bogglingly fast computer systems to record it. The undisputed champion of FRB hunting is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Located in British Columbia, CHIME doesn't look like a traditional telescope. It has no moving parts. It's made of 4 100-meter-long stationary half-pipe reflectors. It simply lets the Earth's rotation do the work, scanning the entire northern sky every single day. Its real power is a custom-built supercomputer that sifts through a torrent of data equivalent to the entire world's mobile data traffic in real time, looking for that telltale dispersed signal. CHIME has become an FRB factory, finding thousands of them. In the Southern Hemisphere, the Australian Square Kilometre Array Pathfinder, or ASKAP, is another key player. It uses 36 dish antennas working together, each equipped with a special receiver like a fly's eye, allowing it to see a huge patch of sky at once. And in China, the 500-meter Aperture Spherical Radio Telescope, or FAST, the world's largest single dish, uses its unparalleled sensitivity to study the faint details of these bursts. So we can find them, but what makes them? This is the central question. The short duration of the bursts means the source must be tiny, no larger than a city. This points to compact objects, like neutron stars or black holes. The leading suspect, especially for the repeating FRBs, is the magnetar. Magnetars are a rare and extreme type of neutron star. They are the super-dense remnants of massive stars. But what sets them apart is their magnetic field. It is hundreds of trillions of times stronger than Earth's, so powerful it can literally buckle the star's solid crust. The theory is that a starquake on the magnetar's surface can cause a violent reconfiguration of these magnetic field lines, launching a blast wave of energy. As this blast wave plows into the surrounding plasma, it creates powerful shocks that generate coherent radio emission, the fast radio burst we see. And in April 2020, we got our smoking gun. A known magnetar in our own Milky Way galaxy, SGR 1935 plus 2154, let out a burst of radio waves. It was thousands of times more energetic than any radio pulse ever seen from a galactic magnetar. While still less powerful than the FRBs from other galaxies, it was the first time an FRB-like signal was definitively linked to a magnetar. It was the missing link. For the one-off, cataclysmic FRBs, theories like neutron star mergers are still on the table. But the magnetar model is currently our best explanation for at least a large portion of the FRB population. Of course, given their extraordinary nature, some have speculated about more exotic origins, including leakage from massive power transmitters built by an advanced alien civilization. While it's an intriguing idea, most scientists agree that the sheer diversity of FRBs and their appearance all across the universe makes a natural, astrophysical origin far more likely. Beyond being a fascinating puzzle, FRBs have become a revolutionary tool for cosmology. For decades, astronomers faced the missing baryon problem. Baryons are just normal matter, protons and neutrons, the stuff that makes up you, me, and the stars. Our models of the Big Bang predicted exactly how much of this matter should exist in the universe. But when astronomers added up all the matter they could see in stars and galaxies, they came up short by about half. Where was the rest of it? The theory was that it was hiding in a tenuous, ionized fog of gas between galaxies, known as the intergalactic medium. This gas is so spread out, maybe only 1 atom per cubic meter, that it's practically invisible. This is where FRBs come in. They are the perfect flashlight to illuminate this cosmic fog. Remember the dispersion measure? It's a direct count of the number of free electrons the signal passed through on its journey to Earth. So, if we can find an FRB and pinpoint its host galaxy, we know its distance. We can then subtract the contribution from our own galaxy and the host galaxy, and what's left is the dispersion from all the space in between. In 2020, the late Australian astronomer J.P. McCart used a sample of localized FRBs to do just that. He established a clear relationship. The farther away an FRB is, the more dispersion it has. Using this, his team performed the first direct measurement of the density of the intergalactic medium. The result was a stunning confirmation. The missing matter was exactly where theory predicted it would be, spread thinly throughout the cosmic web. In one fell swoop, fast radio bursts had allowed us to weigh the universe's normal matter and solve a decades-old cosmic mystery. The study of FRBs is now entering an era of big data. The next generation of telescopes, like the Square Kilometre Array being built in Australia and South Africa, will be the most sensitive radio observatory ever constructed. It's predicted to detect hundreds, maybe even thousands of FRBs every single day. This will allow us to create a detailed 3D map of the universe's matter, test our cosmological models with incredible precision, and answer the remaining big questions. Do all FRBs eventually repeat? Is there a single unified model that can explain their diversity? What is the exact physical mechanism that generates the radio waves? The answers are hidden in those fleeting flashes of light. Each new burst adds another piece to the puzzle. In listening to these whispers from across the cosmos, we are not just solving a mystery. We are using the universe's own lighthouses to illuminate the vast, dark voids and reveal the true nature of everything around us.